Well, hey, AP Bio students, it's Mrs. Shelton here. I am coming to you live from my kitchen, talking to you guys today about the stuff you guys need for data analysis on this AP test. It is actually spring break right now, and this is how, when we are staying home and quarantining, I do spring break. I make videos for you guys. So that is also why my daughter, Sammy, in the back, former AP Bio student herself. She is in the background. She's making some jalapeno poppers for us. So when I am done with this screencast, I'll be enjoying some spicy jalapeno poppers. You guys can ask me in a discussion later on how they turned out. So I'm sure they'll be great. But what we are talking about today is we are doing the first part of our math practice. I have provided for you some exam information. Remember that this year's test is way different because of COVID-19. You are only having two FRQs. Your first FRQ is 25 minutes. Your second FRQ is a 15-minute FRQ. But here within FRQ number one, College Board says that part of this, about 3 points, is this analyzing data piece. So analyzing data is something that is a math practice. It's a practice in biology and in science that's expected. And so here, that's actually practice 5, statistical tests and data analysis. And so what I need you guys to do is in this folder that I have provided for you, this statistical tests and data analysis math practice, I've provided for you the equation sheet that you will be receiving on the test. There's two sides to that equation sheet, and I need you guys to be familiar with all the content that is on both sides. So we're actually going to be breaking this down into two different lessons. We are going to be talking about the first page. The first page is the statistical analysis and probability side. This is the page that's probably going to be new content for you that we haven't really addressed, especially in chi-square analysis is the main thing that we need to make sure that we are going over. And also the use of standard error bars and making sure you can recognize those in graphs. The second page and the second worksheet that I'm going to have you guys do, this rate and growth and everything else, this one you're going to look at and say, oh, there's a lot of content, but it's stuff we've already gone over in class this year, and it's actually pretty darn easy when you actually take a look at it. So this worksheet here, statistical analysis and probability worksheet, this is the one that we're working off of. And I just want to go over some of the content you're going to see in here. And then I'm going to have you guys actually do this. It's a mixture of questions and also a mixture of problems. And then I have provided you my answer key where I have worked out step by step all of the problems too, so you guys can see that. And then we'll also have a Zoom or a Google Hangout time where you guys can ask me questions about any of the math that we have talked about. I've also posted, in case you're not understanding the chi-square test, this Bozeman video is actually a really good analysis just for you guys to take a look at. And then also with standard error bars, also within this folder, there's actually a lot of other videos that I also linked for you as well. So you guys can get a little bit of help. But what I want to address for you is just some of, let's go ahead and talk about just some of the equations and formulas that you're going to see on page 1 of what's referred to as Appendix A and what it's going to look like. And so this is when you print it out, this is going to be what side 1 looks like. And again, get familiar with what content is included here. You will actually see that in Appendix A, when you look at this handout, you will actually see that there's some statistical analysis here. There's this chi-square that's going to be brand new for you. There's some metric prefixes. There's also Hardy-Weinberg equation that you guys have seen. And then mode, median, mean, and range is defined for you too, in case those are asked. Now, linking this back, I do want to just show you. I'm going to move my face up here to the middle. This is actually a summary of Science Practice 5, what College Board expects you guys to be able to do when it comes to data analysis. So in looking at this, you should take a look here that they're asking you to do these mathematical equations that are throughout the curriculum. That's what side 2 is going to be. So when we talk about things like water potential, or if we talk about understanding delta G. Those are going to be some equations that you actually have that are given to you that you know how to calculate. Means, rates, ratios, percentages, basic math practices are expected. Hardy-Weinberg is one of the tasks that they do ask you guys to calculate. However, since we're only covering units 1 through 6, Hardy-Weinberg actually came in unit 7, so I doubt there's going to be a Hardy-Weinberg equation on this year's test. But calculating the mean, calculating the rate of reaction, calculating ratios, calculating percent changes, those are actually really important skills that you guys should be familiar with. Now, this is where I also just told you to using confidence intervals and error bars. We're going to talk about that today and make sure that you are comfortable with using and reading error bars. Now, C, 5C, the skill, perform a chi-square hypothesis test, and also then reject or fail the null, reject or accept, which would be fail to reject a null hypothesis. This is all together what we're going to be talking about today and understanding when chi-square testing is important and understanding these terms. So this is really the new part of today, and then I'm going to also show you some standard error bars in order to make sure that you guys understand how to read those and what that actually means. So let's take a look at, first of all, one of the concepts that you need to be familiar with. Now, one, I need you guys to just know what standard error is. Now, what standard error is, it gives a number value to how precise our mean is, how precise our average is. This is an equation that is given to you. So this stands for your standard error of the mean. That's what this is. And this, what this S is representing is, and this is shown to you, this is your standard deviation that College Board is not going to ask you guys to calculate because it's just an obnoxious calculation and it takes too long and you're not going to have time to do it. But you do need to know what standard error represents. And you also need to know that this down here, this lowercase n, this is number of integers that you have. And so this denominator here is the square root of number of integers. And you guys should recognize that your error is less and less the more data points that you actually have. This is important. But what you are seeing over here is these are error bars that are written. And error bars can be included. We'll actually talk about the 3 different ways error bars can be written. But what College Board will most likely give you is give you a graph with error bars on it and ask you guys to understand what this actually means in terms of how we can trust the data that's given. We can't just give the data in this blue box. We also have to show where our potential error is to see if there's any overlap in our data sets. Now, we understand a mean. Your mean is the average. College Board, however, is going to give you this obnoxious looking equation to calculate what the average of your data set is. So X with a line over it. And so remember that this symbol here, this is a summation. And so what they are trying to tell you here is that you are going to sum up all of your integers and divide by the number of integers that you added up in order to calculate the mean. You guys all know how to do averages, but just make sure that you're not freaking out over an equation because it's written differently than how you learned it in 4th grade. Now, standard deviation. If we take a look at standard deviation, now your standard deviation here, this is an obnoxious equation. I already told you that College Board will, I'm 99.9% confident they are not going to ask you to calculate a standard deviation because it just takes a long time and they know that you only have 25 minutes to do an entire long FRQ. So the standard deviation, this is the summation, and the summation is each variable. So each, ah, no bug in the jalapeno. Oh, get them out. So this is every integer that you have minus the mean, and then you're squaring that, and that is divided by the number of integers you have minus 1, and then square rooting that, and you'll do a sample problem here in order, and I'll show you those sample problems, and you'll figure out that it's not that difficult. However, it just takes a long time, which is why College Board is most likely not going to have you calculate a standard deviation. But what standard deviation shows is how spread out the numbers are, or just this acceptable difference from the mean. So all of this is actually just helping us to understand mean, median, mode, range. So those are all defined for you on your equation sheet too. But it's recognizing that when we have data and sets of data, what we have to make sure we understand is where is the error that that data represents. And that's what all this statistical analysis is for. Now, as far as different error bars, there's standard deviation, which showed you the equation for calculating standard deviation. There's standard error, showed you the equation for calculating standard error. And there's also confidence intervals. I've never seen College Board ask for a 95% confidence interval. What I have seen College Board do is show these error bars and understand that these error bars, we have to assume that our real value is not here at the mean. Our real value could fall somewhere along this error bar. And they might ask you to include error bars. How we use error bars is you take a look and you look to see that there is no overlap in the error bars. If there's an overlap, like here, since there's an overlap here in these error bars, here's my control, here's my experimental group. Since there's an overlap, there might not be any significant difference between these two. So we can't prove, accept our hypothesis is what we cannot do. So make sure you recognize that even though we graph the average, there's still standard error, and there's error bars that then represent where our data could actually fall into, and recognize that if there's no overlap, then there's a statistical significance between the two sets of data. Here, since there is overlap in the error bars, that there is no difference, no statistically significant difference between them. So I gave you a practice problem of calculating standard deviation, so you guys can do that. You can look at the problem set. I explained to you the solution as well, but here's the big dog that we need to be learning about today. This is the most important, and I will bet money on this that College Board is going to ask you guys to do a chi-square analysis. They're not, because this is going to be on a computer this year. They will probably ask you to write the answers, solve it on your own paper, and then type in what your answer is or take a picture and turn that in. Because with chi-square analysis, this is what really separates those who understand data and those who don't. And that's what College Board needs to do on this test with 2 whole FRQs. They've got to know who understands science and data analysis and who doesn't. And so what's a better way to do that? Throw in a couple questions, or at least one aspect of that long free response of ask a chi-square analysis based on it. So here is why you would do a chi-square test. And for those of you who've had stats, you're like, oh, sweet, we know how to do this. This is your equation that is provided for you on your equation sheet. This is chi-squared. It's not chi squared, it's chi-squared. That is always what students will say is, oh, I need help with chi squared. It's not. And this is also not x to the second power. This whole symbol here represents chi-squared, and you leave that number alone once you calculate it. Now, what chi-squared is and why we do this test is we use it to determine if our observed values are acceptable. And that's really just the simple way. But we're also doing it to see if we can accept the null hypothesis. Now, your null hypothesis is a testable hypothesis. This is a number. If we look at in this Mendelian prediction, if I was going to be crossing a heterozygote with a heterozygote, my expected outcome is that I would end up with a 3-to-1 phenotype ratio. That's my expected. So I am saying that in this case, if I had 87 offspring, I would expect 3/4 of them to be yellow and 3/4 of them to be wild type. So my null hypothesis is saying that that is my expected. Now, in this equation, I've got expected values. Expected values are what you would calculate just doing basic Mendelian probabilities or other probabilities. Observed is what actually happened in the lab. So in the lab, here you tested this, you cross these different pea plants together. Your observed is what you then got in the lab. So based on this, the observed were 56 yellow, I had 31 wild type. That means I had a total of 87. So now I've got to apply that, 3/4 of 87. My expected was 65.25. For the wild type, my expected then is 21.75. And so now what I'm going to be doing is for yellow, observed minus expected squared divided by expected. And then I'm going to add that to observed minus expected squared divided by expected. I have 2 different values here. So, or 2 testing situations. We'll talk about that in just a second. So this is why we do it, is to see if the numbers that we get, because observed and expected are never dead on. There's always differences. If I flipped a coin 100 times, I do not Even though I expect 50-50, I don't always get 50-50. And so we need to understand at what point is there something hanky going on there instead of just random chance that I got 45-55 when I flipped a coin. Now, couple things to know when we're doing a chi-square test. Come on. When you're doing a chi-square test, first of all, what we're trying to do is accept the null hypothesis or fail to accept the null hypothesis. So when we say the null hypothesis is that dead-on number of this is my expected. And so if we're accepting the null hypothesis, we are saying that there is no significant difference between the observed values versus the expected values. Now, here's just another example from Mendel. But understand what that term null hypothesis means. Now, there's an alternative hypothesis too. If they ask you what that alternative hypothesis is, that's everything else. That means that, yeah, there was a difference and there's something crazy going on here. And we'll talk more about accepted in a minute. Now, some terms that you need to know is when you calculate a chi-square value, that chi-square number is useless to you, except you compare it to this critical values chart. So you will be given a chart on your equation sheet. There is a chart that is given to you. It says chi-square table. What you have to know is that what the degrees of freedom are, and you also need to know that the probability we use in science is we use this 0.05. All of these other numbers don't matter. They're just there as detractors, so you guys can know that I don't use those numbers. This is the only line, the only box that matters. So we are going to use these critical values. So my critical values that I have are 3.841, 5.991, 7.815, and for you guys, you only have two that's given to you on your College Board equation sheet. They are giving you the 3.841 and the 5.991. Oh, they give you actually up to 8 degrees of freedom. So I doubt that they're even going to give you that now. But it's the 0.05. They do give you a 0.01. But again, that's just to see if you know how to use this chart. Always, always, always 0.05 is where we find our critical value. Now, for each chi-square problem you do, you have to know how many degrees of freedom our particular situation gave you. Now, in that first example where I was looking at dominant or recessive, so I had a dominant phenotype, I had a recessive phenotype. Well, what that actually means is that I had 2 different categories. So my degrees of freedom then are my number of categories minus 1. So in this particular case, if I was comparing my yellow versus, or my round versus wrinkled, or my yellow versus green, my degrees of freedom in those situations would be 1. Number of categories minus 1 is my degrees of freedom. So your degrees of freedom, also then your critical value, these are numbers that you're going to know before you ever do the chi-square analysis. But ultimately what we're doing is once we find chi-square for our given lab situation, we are simply going to be comparing that chi-square value. And again, don't square root that. Once you do observed minus expected squared divided by expected and add that to the next, observed minus expected squared divided by expected, you compare your chi-square value to your critical value. If your chi-square value is less than the critical value, then you accept the null hypothesis, which accepting the null hypothesis is stating that your numbers are good enough. They're close enough, observed and expected, and so your null hypothesis of I expect a 3-to-1 phenotype ratio, you accept that because your numbers are close enough. So you're going to have a practice problem doing chi-square analysis, so do that. I give you an easy one, but again, I give you the observed. You guys have to calculate the expected, and that's something College Board would ask you to do in genetics. That's very much within the genetics was one of the units that is going to be tested, so they may give you some genetics probabilities in here. But with that, you would calculate the expected here, and then do your chi-square analysis. How many degrees of freedom? And are you going to accept or reject the null hypothesis? So make sure you guys practice that. The last thing that you guys are going to do on this worksheet is you're just going to practice your Hardy-Weinberg. Again, just practice it, but chances are really, really low that Hardy-Weinberg is going to be tested because, again, this was part of Unit 7, and this year's test for 2020, just Units 1 through 6. But you guys should feel comfortable with it if in case something gets thrown at you with Hardy-Weinberg. So with that, remember, with Hardy-Weinberg, how I tell you guys to solve, you're always going to be given q squared. Find q then you find p using p plus q equals 1, and then you simply plug and chug. And so those are easy cheesy, lemon squeezy is what you guys are going to think if you were given any of those problems. Now, chi-square though, that's the big piece. Also recognizing error bars is the other big piece that you guys need to make sure that you are identifying. So with that, I will talk to you guys soon. But again, we'll do a chi-squared analysis. We'll do a check-in in order to see if you're understanding that. Watch some of the YouTube videos that I have posted, but make sure you know how to do that data analysis. If you do know how to do it, it's a couple of easy points that you're going to get on your AP test. So with that, hopefully my jalapeno poppers are fantastic. I am looking forward to them, and I will talk to you guys soon. Hopefully you're having a fun spring break just like I am.